In mathematics, a curve is, generally speaking, an object similar to a line but that need not be straight. Thus, a line is a special case of curve null curvature. Various disciplines within mathematics have given the term different meanings depending on the area of study, so the precise meaning depends on context. However, many of these meanings are special instances of the definition which follows. A curve is a topological space which is locally homeomorphic to a line. In everyday language, this means that a curve is a set of points which, near each of its points, look like a line, up to a deformation. A simple example of a curve is the parabola, shown to the right. A large number of other curves have been studied in multiple mathematical fields. A closed curve is a curve that forms a path whose starting point is also its ending point, that is, a path from any of its points to the same point. Closely related meanings include the graph of a function and a two-dimensional graph. History. Interesting curves began long before they were the subject of mathematical study. This can be seen in numerous examples of their decorative use in art and on everyday objects dating back to prehistoric times. Curves, or at least their graphical representations, are simple to create, for example by a stick in the sand on a beach. Historically, the term line was used in place of the more modern term curve. Hence the phrases straight line and right line were used to distinguish what are today called lines from curved lines. For example, in Book 1 of Euclid's Elements, a line is defined as a breadthless length, while a straight line is defined as a line that lies evenly with the points on itself. Euclid's idea of a line is perhaps clarified by the statement, the extremities of a line are points. Later commentators further classified lines according to various schemes. For example, composite lines. In composite lines, determinate, indeterminate. The Greek geometers had studied many other kinds of curves. One reason was their interest in solving geometrical problems that could not be solved using standard compass and straight-edge construction. These curves include the conic sections, deeply studied by Apollonius of Perga, the cissoid of Diocles, studied by Diocles and used as a method to double the cube, the conchoid of Nicomedes, studied by Nicomedes as a method to both double the cube and to trisect an angle, the Archimedean spiral, studied by Archimedes as a method to trisect an angle and square the circle. The Spiric sections, sections of tori studied by Perseus as sections of cones had been studied by Apollonius. A fundamental advance in the theory of curves was the advent of analytic geometry in the 17th century. This enabled a curve to be described using an equation rather than an elaborate geometrical construction. This not only allowed new curves to be defined and studied, but it enabled a formal distinction to be made between curves that can be defined using algebraic equations, algebraic curves, and those that cannot. Transcendental curves. Previously, curves had been described as geometrical or mechanical, according to how they were, or supposedly could be, generated. Conic sections were applied in astronomy by Kepler. Newton also worked on an early example in the calculus of variations. Solutions to variational problems, such as the brachistochrone and tautochrone questions, introduce properties of curves in new ways. The catenary gets its name as the solution to the problem of a hanging chain, the sort of question that became routinely accessible by means of differential calculus. In the 18th century came the beginnings of the theory of plane algebraic curves. In general, Newton had studied the cubic curves, in the general description of the real points in two ovals. The statement of Bezout's theorem showed a number of aspects which were not directly accessible to the geometry of the time, to do with singular points and complex solutions. From the 19th century there is not a separate curve theory, but rather the appearance of curves as the one-dimensional aspect of projective geometry, and differential geometry, and later topology. When, for example, the Jordan curve theorem was understood to lie quite deep, as well as being required in complex analysis. The era of the space-filling curves finally provoked the modern definitions of curve topology. In topology, a curve is defined as follows. Let be an interval of real numbers. Then a curve is a continuous mapping, whereas a topological space, the curve is said to be simple, or a Jordan arc, if it is injective, i.e., if for all in we have implies. If is a closed bounded interval, we also allow the possibility. In other words, this curve does not cross itself and has no missing points. If for some, then is called the double point of the curve. A curve is said to be closed or a loop if and if. A closed curve is thus a continuous mapping of the circle. A simple closed curve is also called a Jordan curve. The Jordan curve theorem states that such curves divide the plane into an interior and an exterior. A plane curve is a curve for which is the Euclidean plane. These are the examples first encountered, or in some cases the projective plane. A space curve is a curve for which is a 3 dimensions, usually Euclidean space. A skew curve is a space curve which lies in no plane. These definitions also apply to algebraic curves. However, in the case of algebraic curves it is very common to consider number systems more general than the rails. This definition of curve captures our intuitive notion of a curve as a connected, continuous geometric figure that is, like a line, without thickness and drawn without interruption, although it also includes figures that can hardly be called curves in common usage. For example, the image of a curve can cover a square in the plane. The image of simple plane curve can have Hausdorff dimension bigger than 1 and even positive Leber's game measure. The dragon curve is another unusual example. Conventions in terminology. The distinction between a curve and its image is important. Two distinct curves may have the same image. For example, a line segment can be traced out at different speeds, or a circle can be traversed a different number of times. Many times, however, we are just interested in the image of the curve. It is important to pay attention to context and convention in reading. Terminology is also not uniform. Often, topologists use the term path for what we are calling a curve, and curve for what we are calling the image of a curve. The term curve is more common in vector calculus and differential geometry. An arc or segment of a curve is a part of a curve that is bounded by two distinct endpoints and contains every point on the curve between its end points. Depending on how the arc is defined, either of the two endpoints may or may not be part of it. When the arc is straight, it is typically called a line segment. Lengths of curves. If is a metric space with metric, then we can define the length of a curve by where the sup is over all and all partitions of. A rectifiable curve is a curve with finite length. A parametrization of is called natural if for any we have. If is a Lipschitz continuous function, then it is automatically rectifiable. Moreover, in this case, one can define the speed of it as and then. In particular, if is a Euclidean space and is differentiable, then differential geometry. While the first examples of curves that are met are mostly plane curves, there are obvious examples such as the helix which exists naturally in 3 dimensions. The needs of geometry, and also for example classical mechanics, are to have a notion of curve in space of any number of dimensions. In general relativity, a world line is a curve in spacetime. If is a differentiable manifold, then we can define the notion of differentiable curve in. This general idea is enough to cover many of the applications of curves in mathematics. From a local point of view, one can take to be Euclidean space. On the other hand, it is useful to be more general, in that it is possible to define the tangent vectors by means of this notion of curve. If is a smooth manifold, a smooth curve in is a smooth map. This is a basic notion. There are less and more restricted ideas, too. If is a manifold, then a curve in is such a curve which is only assumed to be. If is an analytic manifold, and is an analytic map, then is said to be an analytic curve. A differentiable curve is said to be regular if its derivative never vanishes. two differentiable curves and are said to be equivalent if there is a bijective map such that the inverse map is also, and for all. The map is called a reparametrization of, and this makes an equivalence relation on the set of all differentiable curves in a arc is an equivalence class of curves under the relation of reparametrization. Algebraic curve. Algebraic curves are the curves considered in algebraic geometry. A plane algebraic curve is the locus of the points of coordinates x, y such that f equals 0, where f is a polynomial in two variables defined over some field f. If C is a curve defined by a polynomial f with coefficients in f, the curve is said defined over f. The points of the curve C with coordinates in a field G are said rational over G and can be denoted C, thus the full curve C equals C. Algebraic curves can also be space curves, or curves in a space of higher dimension, say n. They are defined as algebraic varieties of dimension 1. They may be obtained as the common solutions of at least n1 polynomial equations in n variables. If n1 polynomials are sufficient to define a curve in a space of dimension n, the curve is said to be a complete intersection. By eliminating variables, an algebraic curve may be projected onto a plane algebraic curve, which however may introduce new singularities such as cusps or double points. A plane curve may also be completed in a curve in the projective plane. If a curve is defined by a polynomial f of total degree d, then WDF simplifies to a homogeneous polynomial g of degree d. The values of u, v, w such that g equals 0 are the homogeneous coordinates of the points of the completion of the curve in the projective plane, and the points of the initial curve are those such w is not 0. An example is the Fermat curve n plus vn equals wn, which has an affine form xn plus yn equals 1. A similar process of homogenization may be defined for curves in higher dimensional spaces. Important examples of algebraic curves are the conics, which are non-singular curves of degree 2 and genus 0, and elliptic curves, which are non-singular curves of genus 1 studied in number theory and which have important applications to cryptography. Because algebraic curves in fields of characteristic 0 are most often studied over the complex numbers, algebraic curves in algebraic geometry may be considered as real surfaces. In particular, the non-singular complex projective algebraic curves are called Riemann surfaces.